Hello, everyone, and welcome to the data stream of this conference, the Big Data Conference 2021. And I welcome you from wherever in the world that you're streaming in today. I'm streaming in from Australia myself. And Einat, I'm assuming you're streaming in from Israel. Is that correct?
Correct.
Yes. So our talk today, Rethinking Ingestion, is going to be presented by Einat, who is the co-founder and CEO of Treeverse. She will tell us a little bit about herself, but worthy mentions are that she has been the CTO of several Israeli startup companies, and she also has a PhD in mathematics. So this is not just everybody we're hearing from today. I'm personally very excited to hear what you have to say, Einat. So over to you to take us through your presentation.
Thank you very much. Hi, everyone. Good morning. I'm happy to be here and to talk about rethinking ingestion, CI and CD for data lakes. Before I do that, I'll just mention that my background is in data. So my PhD in mathematics was utilized to develop algorithms using large sets of data. And later on, I managed organizations that usually had very large data operations and algorithmic challenges. And about 2 years ago, together with my co-founder, Oz Katz, we started the company called Treeverse, who is the company behind LakeFS. It's an open source project that I will talk about a little at the end of my talk, but you can see its lovely logo here on the sides, this axolotl here. But let's dive into rethinking ingestion. So, the architecture that we talk about when you talk about a data lake is an architecture that is based on an object storage such as S3, Google Cloud Storage, Azure Blob, or if you're on-prem, maybe MinIO, Pure. Any form of object storage that is used in order to maintain the large amounts of data that organizations today need in order to analyze and get insights. So this architecture usually, and here there are many options, so I just put around the object storage all kinds of stuff that might be running in your environment. Clearly, it would be only partial to this slide, and there are a lot of technology not mentioned here. But if we look at the left-hand side, we can see data that is being written into the object storage, so the ingestion process that we would talk about today. Either using events that are coming from technologies like Kafka, or if you're on AWS Kinesis or SubPub, if you're on Google Cloud, and so on. And also replications of operational databases, such as data coming from Salesforce, from Zuora, from your marketing. Wherever it is duplicated into the object storage to provide this raw data that is the single source of truth for the organization. Then in order to analyze this data, on the bottom of the slide, you can see the Hadoop ecosystem. So clearly Hadoop, Spark, or either MapReduce if you're still using it, Presto, maybe orchestration using Airflow or any other tools such as Airflow, Hive and Hive Metastore. So many organizations use this infrastructure in order to create data pipelines. On the right-hand side, we can see data exploration. So if it's data science, we would see the notebooks. In this case, I presented Jupyter, for example. And of course, the data visualization tools more used by analysts, such as Tableau or Looker, or there are about 100 more. And at the top of the slide, we can see the analytics engines. Those provide SQL access directly to the object storage, just like Hive does in the Hadoop ecosystem. There are other analytics engines that are actually not from the Hadoop ecosystem. So we can see on the right hand of this box, Dremio, which is an engine over an object storage such as S3, but also works on-prem. And we can see three databases, Druid, Snowflake, and Redshift, Those have their deep storage within the object storage. It means that they have their own storage as a database, but they have another layer of storage that allows uploading external tables into those databases, and that data is held in the object storage. So I hope I was able to convince you that this architecture really has the object storage at its center, and it is very critical for all the work that is done in order to analyze data in most organizations today. And it's really a great architecture. I loved it. I used it as the CTO of SimilarWeb. We managed 8 petabytes of data on S3. Before that, on an Hadoop HDFS cluster on-prem. So really very scalable, very cost-effective. The accessibility of the data is extremely comfortable, and any user almost can do it pretty easily. The throughput is extremely high. And as we saw, and we only saw a partial list of the possible technologies, there is a rich application ecosystem around it that allows to analyze the data and present the data in very many ways. So why are we still talking? Because there are challenges. An object storage is not a database. It provides less guarantees than a database. And if you run a lot of ETLs over it, and you have complex data pipelines or very many sources of data, the manageability of your environment becomes less than optimal or error prone. The reason is that for any need for isolation, for example, you would have to copy data. So let's say now data scientists or analysts want to experiment with the data, to play with the data, and they rather do it on real-life data, so probably production data. They would have to copy production data to another bucket on the side and then do the work there. There are 2 problems with that. If you have very small data sets and not too many objects, it's probably not a problem. But if you need to copy hundreds of millions of objects, then copy becomes a liability. It fails sometimes, right? And the more objects you copy, the probability of that happening to you is bigger, and you get environments that are not similar one to the other. And that challenge is problematic. The other problem is that you start having data lying around from all kinds of copies that people made. And if you, for example, need to comply with GDPR, then forget about the right to be forgotten, because you don't really know what data is where. After all, it's an object storage, and everything is saved under /temp/Einat/final version 2. And it means exactly what you want it to mean, and everyone knows exactly what data is there. So those are the tools that we have, and the only way we can protect ourselves is through permissions. So it's very hard to experiment, to create experimentation environments in an efficient and easy way and maintain them later. It's very difficult to enforce best practices. So if you have decided you want all your data within the object store to be in Parquet or in any other format, if you want to make sure that it adheres to a schema before you start analyzing it, because if it doesn't, there would be problems, then maintaining that could be hard. And the entire set of those limitations create actually an environment where it's hard to ensure high quality of data. And I have scars on my back from trying to deliver quality data over such an environment. So you try and think, what would I need in a perfect world? Let's just try and imagine we need now to ingest, and we will focus on ingesting data into the object storage. And we want to enforce best practices, and we want to make sure that when we expose data to consumers, it is with high quality. So what would we want? And in a perfect world, what we would want, or at least what I thought and my co-founder, is to manage data the way you would manage code, from development to production. So having this ability to collaborate and to move between versions of our outputs very easily in a way that allows us at the end to expose high quality. And if we didn't expose high quality, to very easily revert to a situation where the system is healthy, right? Those are the makings of why we deliver code so much faster. So I wish I could manage my object storage or my data lake over an object storage the way I manage code. What would that mean? How would that look like? So what I would think would be, okay, if I have a quality issue in production, I would want to take my production repository, which is the set of data sets that I am exposing to users, and to be able to revert it to its last healthy situation. Now, this revert allows me to get a synchronized picture of my data between all the data sets that I present. I don't need to revert each one of them. In one atomic action, I get, again, a healthy data lake to expose to my users. It might not be up to date because the latest data is problematic in some way, which is why I'm reverting. But it's always better to have correct data, even if it is a little late, and we have now time to fix the problem. Let's say I want to work in isolation. I'm an algorithms developer, as I told you, today referred to as data scientist. I want to take a bunch of data from production and run experiments over it or check models on it. So I would like to just, in one atomic action that takes no time, create a branch of the data. Clearly, if I'm referring to that so easily, it should probably be a metadata operation, because a data operation would be copying data. So here we would have a metadata operation. We're opening a branch, and we can then play with the data on the side. Once we're done, we can discard it. Sounds cool, right? What else would I need? I would want to reproduce results. So just like I would do in Git, I would want to just go into a commit, which is a version of my repository in the past. Remember, it's healthy, it's synchronized, it's just a point in the past. And if I have developed, for example, a model or an ETL over that data within that commit, I can now maybe run a new version of it so I can compare the results. So I want to have full reproducibility in way of commits. I want to be able to ensure that changes are safe and atomic. So I want to make sure that if I'm now writing a huge data set, no one accesses it before it's successfully done, right? Which is something you can actually do in an object storage, which might be very dangerous. So we want to be able to expose the data only when we know the action is done, and we can do it by merging the data into production only after we know the activity was actually successful. And the last would be if we want to experiment with really large and potentially destructive changes. I want, for example, to try and delete half of my data lake and see what happens. So again, I can open a branch. I can do those terrible damages to the branch. Of course, production at that time doesn't know about this. And I can see what are the consequences of doing those horrible actions. That is extremely important if you want to do chaos testing and try and run all kinds of issues as preparation to production. Again, it's actually a need for isolation, and we achieve that by opening a branch and then running crazy stuff on it. So this is what we had in mind. This is when you try and think of what would be a healthy way to work, those primitives on the right-hand side would allow us to actually create the notion of CI and CD that we know from code, right? Because we have those tools, we have the revert and the branch and the commit and the merge that allow us to now create CI or CD, but not for our code. Our code has its own CI and CD. We are focusing here on CI and CD for the actual data. So it's something between managing the data and managing what is actually the artifacts of our data application, because data is the artifact of our data application. Okay, so how would we be using those to actually achieve CI and CD for data? So let's start with the basic thing of actually having a development environment. So we're not talking about a development environment that can just run small data sets or samples. We're talking about maybe what you would call staging. So we want to develop something new. We want to test it on something that is big data, that is similar to production. And then having this development environment, or maybe a step in the development of a new model. And that development environment should allow us to freely experiment, to be able to reproduce anything that we want through the experimentation process. So I did an experiment, I now want to do a different experiment, go back to the other experiment, compare between them, delete completely the experiment that I've done because I've made a mistake, and go back to my initial data set. And I want to do that all very, very easily. And of course, I want to be able to compare my development environment on one experiment with a development environment on another experiment, maybe comparing that to production, and doing all that in an easy way. That is the first step throughout the development process, allowing experimentation and testing. So just an illustration, you can think of main as being your production data that is exposed to users. And now you can just open a branch, just like we said earlier, this is what you would do with code. Open a branch for experiment 1, open another branch for experiment 2, run both experiments. At the end, you can compare the experiments, decide what you want. If it is the final data set that you would like to expose to users, you could actually even merge it to main. And if you are just updating code, then you now know what you want to do with your code, and you can discard those 2 branches and continue with your life. And there's no data copied lying around anywhere. So that is the safe experimentation. It's the first step in development of data. The second is when we want to integrate or to, let's say, deploy new data. So this is actually the ingest process. We want to ingest a new data set, or to ingest, quote per quote, a new result of an ETL. You can think of that as ingestion as well. And now we want to make sure that the data adheres to our requirements as an organization. So we want to enforce the best practices the organization requires of us. We talked about it could be schema, it could be format, or it could be deeper validations on the quality of the data. So how would we do that? Again, in a perfect world, we will ingest the data into a branch. Just like in applications, people develop code on a branch, a feature branch on the side. We will ingest the data or create new data sets on a branch. Here it's called new data 1. And we will use pre-merge and pre-commit hooks. We know those from Git. So think here, it's a pre-merge hook. Once the data arrives into a new data branch, it would invoke a test. The test can be implemented on any of the systems that you have that run data tests. And if you don't have them, please have them. And then you run your test. If the test passes, the data is automatically merged to main, and it's being exposed to users, to consumers. Or if the test fails, the data is not merged, so your users are not exposed or can't access data that is not in high quality. But you, as the person who's responsible for providing the data, have now a snapshot of the data at the time of the failure to easily debug the problem. So those of you who are running lots and lots of ETLs over object storages know what it feels like to start looking into the data and searching for the actual point in time where something failed or where a problem started. It could be tedious, and it can take a very, very long time. In this perfect world that we're talking about now, I have a snapshot at the time of the failure, and all that is saved, and I can just look at the data that failed and analyze the problem. When I do that, my users or my customers within the organization are not exposed to incorrect data. Of course, the ingestion process doesn't stop. You're not losing any data. Everything is on the branch. Okay, and what would it look like in production? So in production, ingestion of new data is usually, if we are using the continuous integration of data, so input data that we receive from outside into production is already safe. But our production is something that creates data all the time, right? This is where we run our ETLs on our input data. This is where we run our algorithms to assess things. And the actions that production code does on the data creates artifacts of data that are the output of our data application. So here we want to prevent data quality issues. I would show an example in a second. We want to be able to test continuous testing of our data throughout production. And we want to instantly be able to revert if we have exposed our users to faulty data. It's extremely important. It has to be done immediately. The last thing we want is distrust in data, right? So the action of understanding, I now have a problem, I want to revert, should be an atomic action that takes a very short period of time. Okay, some details. So this is just an Airflow DAG, which I assume most of you know, running a few hundred jobs here. So in a perfect world, I would want to have testing after each and every one of those jobs. So I would want to run the job on a branch, get the output, and test it with a pre-merge hook. And when the data proves to be what I expect this job to do, then this data is being merged back. To those of you who want to ask, but I have Airflow, so I can just make sure that the data is not exposed until the test is done. That is true. But where is this data being written to? It's being written to your main or to your production bucket. So yes, maybe you have not exposed it, but it's there and your data users might use it. And in a lot of organizations, when a lot of people are accessing data, there is no way of knowing if the data set that it's already there, it's in its target, right? It's supposed to be there. It's very hard to know whether it was already tested or not because tests are done after the fact. While if you use the mitigation of a branch, then you can be absolutely sure that if data is exposed to users, it is exposed because it is in high quality. So again, the idea of ingestion, but within your production DAGs. Of course, it can also be done with streaming. If you do stuff in Kafka through streaming and then run some logic on the consumers and then save it directly to production on the object storage, then you have those very small batches, micro batches that go in that you need to verify and make sure they run in high quality. So here, not only that you can run tests, but you can also save all information from Kafka, for example, its offset, in a way that allows you, when you revert, to revert not only on the object storage, but also use Kafka's capabilities to revert to the right state of Kafka. This is if you are allowed or if you are capable of saving metadata together with all those beautiful actions that we discussed. So another thing that we would probably want in a perfect world is the ability to save this metadata and to use it when it is needed. And the last very important one is to make sure that when we have a commit or a merge to main, it is a merge that includes all our data sets that are consistent with one another. We don't want to have, I'll give a very naive example just so you understand. We don't want to have marketing data from that starts in 2 p.m. and sales data that starts in 1:58, because that would create discrepancies within the two data sets that may hurt our results. So we want to make sure when there is a commit, it is a commit of consistent data sets, which is why we can use branches in order to ingest each and every one of the data sets to its own branch. after they are tested, we can merge them to another branch that includes other data, or to a whole new branch, depending on your branching policy. And then with one atomic merge that to production. So it is now one commit on main that we can always go back to, and it is reproducible and consistent. Complexity of asynchronization could happen not only from different ingestion origins, it could also be because of jobs that are running and writing outputs. And those may be late, and so on. So there's a lot of synchronization that we need to do, and the abstraction of branches allows us to easily do that. Okay, so after we were all very much convinced that having the ability to CI and CD data, and I hope I have managed to convince you that would be a very good practice. Some of you probably have it already, but it is, if you are over an object storage, it is probably based on quite a lot of copying. I've seen that in several organizations where they have a dirty bucket and then a clean bucket. But it means that every data set is being copied. And as we discussed, copy of a lot of data can become tricky. And all that requires quite a lot of DevOps support. So as I mentioned earlier, we have experienced that while I was the CTO at SimilarWeb, and this was where my brilliant co-founder came up with the idea of LakeFS, of actually an abstraction over an object storage that makes it atomic and versioned. So now our data lake is atomic and versioned, and we can behave as if we have Git over the objects in the data lake. And this is LakeFS. It's an open source project that we have released about a year ago, and it is now being used by quite a few companies with and also very nice brands, and we will reveal them soon. How does it work? So basically, it wraps the object storage. It provides an interface to the object storage by a client, or need be by a server or gateway. And that interface allows you to use all the applications we've already talked about. And I think a few we haven't talked about are already mentioned here, full list coming soon, to actually access our client and then perform all the actions you would usually perform over your data lake, but also perform Git-like operations that we talked about we would love to have in a perfect world. So you have on the right-hand side, you'd be able to do all the API compatible calls. We support, as you can see, S3, Google Cloud Storage, and Azure. S3 in general, not only the Amazon one, so any object storage that supports the interface of S3, MinIO, for example, Pure, for example. And on the right-hand side, you can also use an API that is very much Git-like, branches, commits, merges, all done with metadata operations. I'll explain a little more in a second. And in the middle runs a versioning engine, which is actually the heart of LakeFS. All the logic of how to actually create a Git-like experience over an object storage lies there. It's open source, so you can look at the architecture, look at the code, and understand exactly how it works. Its power is that it is extremely scalable. Of course, Git wouldn't work here, because the way Git works is that it's human scale. It comes to support a problem where people need to communicate and collaborate over code, while here we talked about Kafka, we're talking about thousands or tens of thousands of jobs that may be running daily. We want to be able to support machine scale. So it's a different problem and hence a different solution. But when you are a user, it's actually very simple. All you need to do is change the path that you are now using to access the data. Instead of directly accessing the bucket, you would now also mention either the name of the branch that you are accessing or the number, the commit ID. And you could then access data at a certain time point or a certain version of it. And it integrates with all those beautiful tools. So here the list grows, and you can see additional tools that I haven't mentioned before. It's very easily adapted to technologies. So if you want to use LakeFS and you have a technology and you're not sure, just ping our Slack channel, and we will be able to probably help you get it supported very quickly. How does it work? So at the beginning, I said in a perfect world, I don't want to rely on copying, because copy is a problem, and also it creates, instead of a data lake, a data swamp. So we want to avoid copy, and in order to do that, we use metadata. So when you have your main branch or your production branch and you want to now start a branch from it, the action is a metadata action. It would create pointers to the actual data in main. Okay, this is why when you look at S3 here or at any other object storage that LakeFS runs over it, you see the pink part, which is the actual data. And you see the metadata itself. The reason we're saying the data is deduplicated is because when you open a branch, we do not duplicate the data, we simply create a pointer. When would a new version be created? Let's say we ran a job over the branch and we are now writing on the branch a file that already exists in main. In this situation, we would be using copy on write of the storage, and another version of that same data set would be created. The branch would be pointing to the new data set, while main would still be pointing to the old data set. And here we would have two versions of the same data set. And the amount of versions that you want to save of data sets is something that you can decide on, and you can run garbage collection and clean your data lake and delete data or versions that are not needed very easily through LakeFS. I am being asked a lot whether it increases the cost of your object storage. So usually it actually reduces the cost because people stop copying. So in order to get isolation, you need to copy data, no more. You don't copy data. So although you save versions of what you actually need, and you do not copy again and again data that is similar to what you have in main. So usually there's actually a reduction in cost, but that is not the reason to use LakeFS. The reason is the manageability and the ability to be very efficient as a data engineer, a data scientist, or an analyst. Okay, let's move to the left-hand side in the drawing now that we understand why we see in S3 both the data, the deduplicated data, and the RocksDB that holds the metadata. Those are all those pointers that we talked about. So what we see is that we have two options here. One is using the metadata manager that is communicating with the LakeFS client. It doesn't have to be an Hadoop client. It can also be just your own Python code that is calling LakeFS. We have an SDK for Python or for Java, Scala, so on. So what you would want to do is use our client. And then the client is calling the metadata manager just in order to resolve paths, because you are calling /main/ something or /my branch/ something, but the data within S3 is actually saved in a deduplicated way with different paths. So the metadata manager would be the one replacing the LakeFS path with the actual S3 path, and then the client would be calling the S3 directly, again, or Azure Blob or Google Cloud Storage, but the data would be called directly through the object storage, so and of course would be returned back directly to the application that holds the client. In case no client exists, and that rarely happens, Then you can use LakeFS as a gateway, and then both the data and the metadata go through our gateway. And the data is saved and returned through the gateway capability. So this is how it works, and we have a very simple local integration you can do, or just, an installation you can do. So you can locally run LakeFS and just enjoy the capabilities and then understand or decide how you want to use them. And if you want to run directly on the cloud, you can use the Helm chart, of course, if you have Kubernetes, or a native cloud installation that also exists. Another thing I can talk about, I'm not sure I have the time, I'll do that really quickly. This is the data format of the metadata. So it is actually a layered, it has 3 layers. It is a layered list that calls a list in a way that allows us to represent the metadata in an efficient way. This is important if you have very large merges or very large diffs. I don't have time to go into the details here, but it is all documented very well in our documentation. And the need for this data structure is, again, the performance of diff and merge. We want that to be linear in the number of changes that are made to the data. By the way, if you run a critical path action, such as calling data, reading or writing data, then the overhead is very, very small. It's around 10 milliseconds. When you perform a very large merge, it can take longer, but it is not a critical path action that calls the actual data. More about that in our documentation. And here are additional resources, so you can just go into our docs and get started. And of course, you can join our Slack channel and ask any question anytime. The community loves getting new members and helping them. And if you want to contribute, that would be awesome. So you have the repo here as well, or just look at the code. And I'll be happy to take questions now. I hope that would be enough time.
Einat, thank you so much for that very informative presentation. Really enjoyed it, and I hope the audience as well enjoyed it. And we had very high attendees all the way through, so I think that's a good sign. Now, everyone in the audience, please ask your questions in the Q&A section on your screen. The more questions you ask, the better answers you're going to get from Einat. And we have our first question from Marcos, who asks, can LakeFS keep the object store in HDFS or only in AWS S3, Azure Blob Storage, and Google Cloud Storage?
So we currently don't support HDFS as a storage layer, but we do intend to do that because some organizations have already spoken to us about that. It is not very hard to do. We're just adding another storage layer to the code. So if you're interested, just go into our Slack and let's discuss. And we can support HDFS.
And we also have a question from, so thank you for that question, Marcos. We have a question from Azad, who says, is there a more abstract paradigm between data layers? How can we apply CI/CD to recalculate data between ODD and DDS layers, for example?
ODD and DDS? I'm sure I'm not familiar with the acronyms. Can you please explain?
Well, you won't get an explanation from me necessarily either. So we might hold that one over unless. Okay.
I'm sorry.
Expands on it.
I would love to answer. You can ping me personally on Slack or on LinkedIn. I'm sorry, I didn't understand.
We have a question from Artyom, who asks, what kind of integration do you have with Snowflake?
So that's an excellent question. We currently don't have an integration with Snowflake yet. If you are interested in that, because we already, again, have a few users who are interested. So if you're interested in that, please join our Slack channel and let us know. We will interview you about the needs, and we will have support for Snowflake in a few months. And you can share your inputs and your requirements and influence how it's going to be implemented. That's the joy of open source. We can do it together, and we can do what you need.
Now, Einat, here's a challenge for you. So you said you couldn't do it in a short time, but Christoph has put the challenge to you. Given that there is some time left, could you quickly elaborate on the metadata structure again? In 4 minutes.
Sure. And is there another question?
That's it for now.
Okay. So, of course, I'd love to. So the way it goes is that we save the metadata. Actually, in object storages, the hierarchy doesn't really exist, right? Everything is lists. It's not a file system. And then what we do is we list the objects, and we create a tiering where there is an ID of a range in the first layer that is in the second layer reflects an in-between set of ranges. And that goes through 3 layers. So it allows us to pretty quickly drill down through that hierarchy to get to a place where there was an actual change. And then when we compare 2 different branches, we can see what layer of ranges was changed, and only compare those small lists that we have identified out of the entire large tree to understand what the diff is, and then present the diff, either for merge or just as a diff. So to see if there are if the merge is not clean, then to see the collisions between the changes and present that. That's in a nutshell. And yeah, it took me 2 minutes.
So well done. Now, unless there are any more questions, I'll give everyone 20 to 30 seconds to think up any questions that they might have for the last 2 minutes. But unless there are any questions, Einat, is there anything else that you would like to get across? Perhaps how listeners can get in touch with you after this?
So I had this out the entire time. So if you write LakeFS on Google, you would be immediately a Lakers fan. We're working on that. Once LakeFS is very successful, when you look for Lakers, you would find LakeFS. But until then, mind that you are just using lakefs.io, and you will get to our website. Again, open source, mature, running in production in very large organizations. And we will be happy to have you in our community and to hear what you need, and so you can help us shape the right product for you.
I think that's a great open invitation for some open source collaboration. Einat, thank you so much for presenting to us today and sharing your knowledge. Really helpful for me, certainly. So I'm assuming the audience got just as much out of it. I hope you have a nice day today and continue to enjoy the conference. Now, for everyone listening, we now have a morning break. So we have 15 minutes till the next line of presentation start, which will be 5 minutes past the hour. So until then, enjoy yourselves, and we'll see you again very shortly. Thank you, Einat, again.
Thank you.